Hi everyone. Today I'm going to be explaining project 5B in some amount of detail. This project, at least in my personal opinion, is a lot easier than P5A, and I'll hopefully help you see how it's sort of relatively easier and will help you at least get started on the project. So in project 5B, your task is to sort of modify the x86 file system to add mirroring. You already learned in class that mirroring is used for redundancy. So you are sort of like the thing to do in this project is to basically mirror every block that you write to a file, so that there are two copies for every logical block, and on a write you just write both copies, and on a read you read in both copies, and you return -1 if they're both not the same. Okay. Sounds pretty simple, right? We'll see how we can actually do that. There's also some amount of detail that you'll have to do. You'll have to modify the stat system call, so that it prints out the logical and physical size. You'll also be adding a new file stat program that actually prints out all the physical blocks that are allocated to a file, so that you know if you have a mirrored file, what are the different blocks that are allocated to a mirrored file, versus if you have a normal file, you just see that there's like one copy of each block, whereas in a mirrored file it will show you all the different copies. So let's get started. So the first thing to sort of do when you're doing this project is to get familiar with the file format in x86. It's actually pretty simple. Let's go look it up. So let's see, include. All right. So this is sort of the structure of the file system. So block 0 is not used, block 1 is the super block, inodes start at block 2. Most of this is information that you'll not be using directly. You will be using information about the number of direct blocks and indirect blocks. So there are 12 direct blocks in the inode, and after that there is one indirect block, so that uh, you can use that block to keep more pointers to your direct blocks. So you have the maximum file size defined here. Let's see, what else do we need to do here. A lot of it is stuff that we will not be touching. So one thing that you should note is that, let me see, right. So here we are defining all the different kinds of files in the file system. So there is the directory file, there is the regular file, and there's also the special device like dev0 random, if you've used that in Linux. So here we'll actually be adding a new type of file to the system, like so. And the point of this is that while we do want mirroring in the file system, we don't actually want to do it for every file that is there. And the reason for this is we want to incrementally build the file system. If we just like turned on mirroring for every file that is there, you'd have to make sure that you hit the bootstrapping code, all the files that are used when you're first booting up the kernel. It becomes a huge pain. So for files which are of type 2, the t underscore file, we're just going to say that's going to work as before. We're not going to touch that at all. For files which are of type 4, which are t mirrored, we're going to say we're going to use mirroring. Okay, which means that they'll have two copies for every logical block that's seen by the file. So we'll be doing that. So back to the description. Let me see. Right. So how the way we want you to implement mirroring is very simple. So let me just like type it out here. So let's say that your inode has a number of pointers, right? So there's like pointer 1, well, let's say this is your inode, and then there's a number of addresses like address 1, address 2, address 3, and address 4, and so on. So this is how a normal a regular inode will look. What we want you to do is we want to say in a mirrored file, this will be logical block 0, and then address 2 will be the second copy of logical block 0. Okay. Similarly, in address 3 we'll have the logical block 1, and here we'll have another logical block 1. Okay. So even though you have 2 slots, you're actually using up 2 slots for the same logical block. Okay. So in this way, the maximum size that your system can actually address is going to be lower than that of a regular file. A regular file will be able to do whatever is the maximum size, like direct pointers, 12 direct pointers plus your indirect block. Here we'll only be able to do half of that, because like we're saying, every 2 pointers in your inode is going to be used to store the physical copies, the mirrors of the same logical block. Okay. One important thing to note here is that, like, if in this particular mirrored inode, if we wanted to read logical block 1, we should go to the 3rd slot, or if we are using indexing, to index 2. Okay. Previously we used to go to index 1 to get the second block, and this is something that we'll have to change. Okay. And that is actually present in, I believe, fs.c. Okay, so this is a function that you'll have to modify so that you can do this sort of like translation more easily. And we'll see in a little bit of time where bmap comes into the picture, as we sort of like go through this logically, but we'll come back to bmap. Okay. Let me see. So in stat.h we are going to add the new kind of file tmirrored, which will have the numeric value 4, and so on and so forth. And of course, you'll also have to add o_mirrored flag to the open file. So let's go look at that. Let me see. So let's add tags. So let me see, what do I want to do? Let's go look at open. Okay. So see, remember that here we have, when you're creating a file, you can specify things like create and so on and so forth, right? So similar to that, we want to create a new flag. Just like create, we want to say something like o_mirrored, and that's going to have value 400. Okay. So if we pass in this flag to create, it means that, or sorry, to open, it means that we are opening a mirrored flag, sorry, a mirrored file, and we expect that something will be different for this file versus your regular files. Okay. So you'd use this flag back in your sysopen, so that you'd be doing something differently based on, for example, in here we're just creating a normal file, right? You'd want to create a file with t_mirrored sort of at this point. Create, if you go look at it, will just like set everything up, and then it'll set all the types of the file up, and then it'll set the number of hard links to a file, the major and minor number, and so on and so forth, and then just return the inode pointer. So we want all of this to be done, but we want it to be done for t_mirrored in addition to t_file. Okay. So that's something that we'll add in here. Make sys_open, which is basically your open system call. Be cognizant of the fact that there's a t_mirrored, In order to do that, have an O underscore mirrored flag to the open system call. Okay. There may be a slight confusion with the O underscore mirrored and T underscore mirrored. O underscore mirrored, or in general O underscore whatever, is all the flags that you pass to open, right? So that's seen by user level code. So let's look at some user level code. Let's see. Um, let's see. Stat ls maybe. Um, let's see. So O underscore create user star.c. So sh.c. Okay. So if you look at it here, you can actually see flags like read write and o create being passed to different commands here. So the O underscore stuff is something that's seen by user space, okay? Whereas the T underscore stuff is all seen, it's internal to the file system. Like T underscore file and T underscore mirrored is all things that are used inside the file system, inside the kernel, to sort of keep track of like the different kinds of files that are there. So that's not seen by or that's not directly used by anything in user space. Okay, so that's why we have two different sort of like things, T underscore mirrored and O underscore mirrored. Okay, all right. So in order to do this project, you should probably start by looking at something like sys underscore read and sys underscore write. So these are the functions or the system calls that are used to read and write to files. Okay. And so if you sort of like go into these things, it goes to file read, for example, and it does pretty much what you would expect. If the file is not readable, return -1. If it's a pipe, do a piped read. If it's actually an inode, lock and then do a different function, a read-i function. Now the reason there's locking here is that there is one offset value per file, right? If you have two threads which are reading the same file, both of them will be trying to update the offset value. So we want to lock it to make sure that the offset is updated correctly. Okay. So let's go to see read-i, which is sort of the heart of the matter. So in read-i, if it's a device, we do certain stuff. If it's not, we actually get to the meat of the matter. Once again, we say that if you're trying to read something that's beyond the size of the inode, we return -1, or if like while we're reading this, we will fall off the end of the offset, or like if the offset is like too large of a value, we return -1 also. Okay. And if we find that if we read n characters, if it's beyond the size of the file, we trim it to the size of the file. Okay. And this is sort of the key part. So they're using something called a bread function. Okay, so the bread will basically you give it a device, the inode, the device that this inode is associated with, and also a block number, and then bread will just read that in for you. Okay, so it's a very simple sort of function. Give me a device and give me a block number, I'll go read that block for you and then put it in this buffer. Okay, so in order to do this, they are actually using another function called bmap, and bmap is like sort of very important to us. And what bmap does is, if you give it a particular inode and a particular block number, it will return the physical block on disk where this logical block is stored. Okay, so to sort of give you an example, an invocation would be something like this: bmap, let's say inode pointer of 0 would, for example, give me 100. That means that the first block of the inode is stored in physical block 100. So bmap is the guy who knows how to do this particular translation. Okay, now that means that you will have to modify bmap in order to get our work done, right? Because we are modifying the translation, right? So for example, previously it used to do bmap IP1, it used to go and look at the second array in the inode, the second direct pointer in the inode, and then return 101. But for a mirrored file, this is obviously not true. Like both 100 and 101, both are copies of the same logical block. So you'll actually have to go look at so bmap of IPF1 should go look at the second direct pointer. Okay, so there needs to be some sort of like translation going on there. So if you look at the bmap function, it's very simple. Like if it says if the block number that you give me is less than the number of direct pointers, I'm just going to look inside, and if it's 0, meaning that there is nothing that's allocated there, I'm going to do an allocation. Balloc just allocates a block for you, and then returns that address, and then that puts it in the direct pointer, and then returns the address. Okay. So if it's not if the block number is beyond 12, meaning it's an indirect block, then we do slightly more complicated stuff. We go look at, we first read in, bread is just a function that reads in the block, so we read in the indirect block, then we use that to look at like the other blocks that are there in the system. Okay, so you will have to modify bmap so that for mirrored files, and this is key, you don't want to change this for every file. If the file is a mirrored file, and the way to sort of check that is IP will have something called a type parameter. Okay, and that will be either t file or t underscore mirrored and so on. Okay, so check for that, and then if it's t underscore mirror, you'll have to do something else. So in my implementation, I just had a different function for bmap. Okay, so in the normal bmap, you always, when you're given a block number, you just like return one address. But in our sort of mirrored bmap, what I did was I had an additional parameter which specified which of the mirrored copies do you actually want, right? So you can imagine something like, let me write that down here. So you can imagine something like a mirrored version of the bmap, which actually takes the inode pointer. Let's see, struct inode star IP, a uint logical block number, and a uint for the copy number. Okay, and this is key. So because like let's say we did something like mirrored bmap IP, and then we said we want the logical block 0, but we want copy 0, so that's going to resolve in our running example to 100. But if we did the same thing and then we said we want this to be 1, that's going to resolve to 101. Okay, what internally mirrored bmap really needs to do is going to look at the different direct pointers in your inode, and then just resolve that directly to whatever it is that we're giving you. Okay, if you think about it, it's not really hard logic. We just need to calculate the indices sort of like intelligently. It's not really hard to do. I'm sure you'll figure that out. So now that you have written sort of like a mirrored bmap function, then you can use that to write mirrored versions of write I and read I. Okay, so for write I, coming back, for the regular versions, we are just saying you do a bread, and then you move your data from your source into this destination, then you write that particular buffer, and then you release that buffer. The release is so that like you pin it in memory so that you can't release a buffer that somebody is looking at. Okay, so in here you'll basically have to do this for every copy that's there in the system. Okay, so just do a loop and then do it for copy number 0, copy number 1, and so on. And instead of using bmap, you'd be using our mirrored bmap. So you'd be saying, I'm going to get me the block number for copy 0, or get me the block number for copy 1. Okay, so if you use mirrored bmap here, you'd actually be getting the block number that you desire, and all the rest of it doesn't need to change, like, because we're doing the exact same thing in every block. It's just the block number that changes. Okay. So you'll need to do something like that for write I, and then you'll be doing something similar for read I. Okay, the change will be that in read I you're going to do, let's see, where is read I? So in read I, the difference is going to be that instead of like doing multiple, you'll of course be doing multiple reads, but you'll have to compare them to see if like they're correct or not. So you can just use string comparison to do that. The result will be in your destination buffer. So every time you read a block, just check for that and then see if it's like different or not. Once you have figured out how to do write I think doing read I will not be terribly different. You just have to use mirrored bmap as before. So interestingly, I haven't actually talked about things like, do you actually have to change BLOC, right? Because I'm seeing some people sending mail to the list saying, do I need to change ILOC? Do I need to change BLOC? So if you do something similar to what I've been saying, we are actually taking advantage of all the BLOC stuff that's already in there. The inode is just going to say, I'm going to need a new block, and then bmap is going to request that, right? and all of that stuff is going to remain the same. So your inode, as before, will just have a list of like addresses. It's just that how we interpret those addresses while we're doing read I and write I will be different. So you actually can get away with not changing BLOC at all. Okay. So what I've told you is sort of like the sort of heart of the matter. If you do all these changes, you should be able to figure out all these side things that you need to do. Let's see, what else do you actually need to do? And of course, you don't need to do any of this for your directories. Okay, so it's just like your T file, your regular files, and your two mirrored files. Okay, so you will have to modify stat with the new structure that we give you, so that you report the logical size and the physical size of it. So this ideally shouldn't really be hard. So if you look at it, I think this was in sys file. Let's see. So so there is actually an fstat system call which already does most of the work for you. all you really need to do is like, you need to call stat I, and then you need to modify it so that it updates the new fields in your stat structure. The only sort of like painful thing to do here is that we've changed size to be logical size. So you just have to find all the places in the code where they say stat structure points to size, and then change to points to logical size, and then you have to calculate physical size, but I'm sure you can do that. You can do that at this point. Okay, so that shouldn't take a lot of time for you. It's like a few lines of code change everywhere. Okay, finally, there's also, you'll have to create a new program called filestat, which shows you all the different things that you use in your code. Let me see if I can show you. Oh, the connection is gone. So let me show you what my file stat looks like. It doesn't have to be super pretty. CD projects P5B working XV6 make QEMU Nox. So mirror is sort of my test. It'll write a test code, and then let me see, file stat foo2. I think that's the sort of the file that I'm looking at. So if you can look at all the different things that I'm writing in foo2. So basically, I'm typing out the I'm printing out the type of the file. I'm printing out the logical size and the physical size. As you may have guessed at this point, all of this stuff I'm getting from the stat structure. Okay, the really hard part, or like the different part that we're doing, is how do we get all these block numbers that we have here. And the way I did it was, I just added a new system call which sort of interfaces with bmap. Remember that our mirrored bmap, let's see, our mirrored bmap, if you give it an inode, a logical block number and a copy number, it will tell you what the sort of like block addresses. So all I did was I built a new system call that sort of calls mirrored bmap given the file descriptor. So once you do that, then in user space code, you can just like get the maximum size of the file, then loop around like for every logical block that is there in the file, call the system call for every mirrored copy. Okay, so by doing that, you can actually get all of the different blocks that are present in the in the file. Okay, so if you think about it, you just be calling mirrored underscore bmap for every logical block and sort of like mirrored copy that's present in the file system. So just loop through that in user space code, get the block address, and then just print it out. So adding the new system call is a little bit of a pain, but then it just directly calls mirrored bmap, so it shouldn't be too much of a problem. Okay, you do have to make sure that file start works with both t underscore file and t underscore mirrored, meaning that if you call file start with a regular file, it should just print out like one copy for every sort of logical block that's there in the system, and it shouldn't crash because it expects more copies to be there. Okay. So presumably, if you have done all of this, the extra credit should be relatively simple. Instead of having 2 copies, we're going to store 3 copies. And if there is a problem or a mismatch, all we're going to say is, we're going to, on a mismatch, we're going to say, we're going to look at what is the majority among the copies that we have. And we're going to rewrite the mismatched copy with the information from the matching copies. So we have 3 copies and 2 of them have value x and 1 of them has value y. You would overwrite the y with the x, okay, and then you would return x on a read. So that's what you have to do here. All right, hopefully this has been useful, and it should help you get started on P5B. My hope for you is that this is relatively simple, and then you shouldn't be spending like 20 hours on this like some people apparently did for P5A. Okay, send questions to the mailing list as usual, and we'll be glad to help out.